to section 1 is about torque. First, we need to differentiate between a point mass and extended object. When we study the linear motion of an object, we consider the object as a point mass. What do we mean by this? It means the shape of the object is not important. We consider it as a single point, but the shape is not important. What about an extended object? An extended object is when we study the rotational motion of an object, we consider the object as an extended object. What do you mean by this? It means the shape is important and we have to take it into account. So the shape is important. Examples for these two are, for this one, a sliding box. Let's have an incline and we have a box. We choose multiple points on this box and slide down. We see that every point will have the same velocity. So if I study the motion of a single point, it will be correct for all other points. Any object that are in free fall or in circular motion, they are all considered as a point mass. Examples for extended object. Any object that is rolling, spinning will be studied and calculated as an extended object. Why is that? Because if we have a rotating object and we choose two different points, we see that they have different linear speeds. So if I calculate one of them, I cannot say that the other point have the same linear speed. So I have to calculate each point separately. So this was a point mass and this is an extended object. Let's have a ball that is rolling toward a goal or rolling down an incline. It is rotating and moving in a straight line at the same time. Because of this one, it has rotational motion. Because of the linear speed, it has linear motion. When an object is rolling and it has linear motion, we call the linear motion of a rolling object as translational motion. So translational motion is the linear motion of a rotating object. So what should I do here? Should I consider it as a point mass or an extended object? If I study the rotational motion, I have to study the object as an extended object. But if I study the translational motion of the center, I have to take it and study it as a point mass. Do you have some other examples? Yes. Earth around itself is rotational motion, but Earth around Sun is a linear or translational motion. So you have to take it as a point mass if you study the motion of Earth around Sun, and you have to study it as an extended object if you study the rotation of Earth around itself. Now, what should I do if I want to rotate an object? If we remember from chapter 1, section 3, we talked about that if we want to speed up an object, slow down an object, move an object that's at rest, and stop a moving object, we need to apply a force. So here, what should I do to rotate an object? We need a quantity that is similar to a force, which is called as torque. So we can say that torque is the rotational analog of force. It has the same job as force, but in rotational motion. So we can say that if we have a torque, we can rotate an object. If we have a torque, we can stop a rotating object. If you have a torque, we can speed up and slow down a rotating object. We can also define torque as the ability of a force to rotate an object. It means that we still need a force to have torque. So if a force can rotate an object, it has torque. If it cannot rotate an object, it has no torque. Torque for that force will be equal to 0. To have rotation, the first thing that we need is an axis of rotation, then we need a force. Let's have some examples and let's see if we have a torque or not. Let's say this is a door or a window, and this is the hinge or the axis of rotation. If we apply multiple forces on the hinge, will you be able to open that door? Of course not. So the torque here will be equal to 0. This force has no ability to rotate this object. So I need to apply the force away from the axis of rotation. This is the hinge, the axis, and I will apply a force in another way this time. Try to move the door like that or like this. We are applying a force at a distance from the axis of rotation. Can we rotate this? Of course. You can try it at home. You cannot rotate this door either. So the torque here again will be equal to 0. In the first case, distance was equal to 0 because we applied the force on the axis of rotation. So the distance from the axis of rotation on the axis of rotation is equal to 0. But on the right side, you can see that we have applied the force at a distance, but the angle here is equal to 0 because they are parallel. Both of them are parallel, and the angle for this one is 0 degrees, and for this one it is 180 degrees. So here we can say that the force is parallel to the distance. As a result, it couldn't rotate the door or the window. So I need to apply this force at a distance, and the force must be perpendicular. Let's see if we can rotate it or not. If you apply a force perpendicular to a distance, you can see that you can rotate it very, very easily. It means the torque is maximum. You have the maximum ability to rotate this door, and the torque here, maximum torque, will be equal to force times distance. What happens if I apply the same force, but this time with an angle between 0 and 90 degrees? Now, this force has two components. One of the components will be parallel, one of the components will be perpendicular. Okay, this will be perpendicular and this one will be parallel. So I will call this one as parallel component, and I will call this one as perpendicular component. Because of which one will we have a torque? We said that the torque of this one is equal to 0. So because of the perpendicular component, you'll have a torque. And torque in this case will be equal to the force multiplied by distance multiplied by, should I use cosine or sine? As you can see, this component is attached to the angle. So this one is cosine and this one is sine because it is not attached. Any component that's not attached to the theta is a sine component. So in the equation of torque, I will have sine theta. But remember that the angle that we use must always be between the force and the distance. Don't use any other angle. This d sine theta has a special name. This is called as lever arm. And instead of taking the perpendicular component of the force, it is taking the perpendicular component of the distance. So lever arm is the perpendicular distance from the axis of rotation to the force, to the point where the force applied. I will simply write it as to the force. It has another name, which is called as moment arm. The unit of torque is Newton times meter, because the force is Newton and the distance is meter. Okay, you may have seen this in grade 11. This is similar to the equation of work, which is equal to joule. So this one, is it also equal to joule? But the answer is, of course, no, because torque is a vector quantity and work is a scalar quantity. Another difference is that in the equation of work, you have cosine, but here we have sine. If the rotation is in the clockwise direction, the torque is negative. If the rotation is in the counterclockwise direction, then we will take the torque as positive. What should we do if we have multiple forces acting on an object at different distances? Should we find the net force and calculate the torque? Of course not. We have to calculate each torque individually first and then calculate the net torque. So let's say this is the axis of rotation and we have multiple forces. This is distance 1, distance of F1, this is distance of F2, and this is distance of F3. I can use all the angles that I have in this example because this one is between the distance and the force. This angle is also between the distance and the force. This angle is also between the distance and the force. So I can use all the angles without using cosine or any other thing. Net torque here will be equal to torque 1 plus torque 2 plus torque 3. And each torque will be equal to force times distance times sine theta. So if you have multiple forces and multiple distances, that's how you calculate the net torque applied on that object. That's all about section 1.